Breakthrough, Groovy Key to Nanotubes in 2D. I'm Steve Belair, welcome to Breakthroughs. Ultrathin carbon nanotube crystals could have wondrous uses, like converting waste heat into electricity with near-perfect efficiency, and Rice University engineers have taken a big step towards that goal. The latest step continues a story that began in 2013 when Rice's Junichiro Kono and his students discovered a breakthrough method for making carbon nanotubes line up in thin films on a filter membrane. Nanotubes are long, hollow, and notoriously tangle-prone. Imagine a garden hose that's dozens of miles long, then shrink the diameter of the hose to the width of a few atoms. Anyone who's ever fought with a knotted hose can appreciate Kono's feat. He and his students had turned a mob of unruly nanotubes into a well-ordered collective. Of their own accord and by the billions, nanotubes were willingly lying down side by side like dry spaghetti in a box. The problem? Kono and his students had no idea why it was happening. It was magical, really mysterious, said Kono, an electrical engineer, applied physicist, and materials scientist who studied carbon nanotubes for more than 2 decades. We had no idea what was really happening on the microscopic scale. And most importantly, we did not even know in which direction the nanotubes would line up. He and his team published their findings in 2016, and the field weighed in on the possible explanations. The answer, as described in a new paper by Kono's team and collaborators in Japan, is both unexpected and simple. Tiny parallel grooves in the filter paper, an artifact of the paper's production process, caused the nanotubes' alignment. The research is available online in the American Chemical Society journal, Nano Letters. Kono said a graduate student in his lab, study lead author Natsumi Komatsu, was first to notice the grooves and associated them with nanotube alignment. I found that any commercially purchased filter membrane paper used for this technique has these grooves, Komatsu said. The density of the grooves varies from batch to batch, but there are always grooves. To form the 2D crystalline films, researchers first suspend a mixture of nanotubes in a water surfactant solution. The soap-like surfactant coats the nanotubes and acts as a detangler. In 2013, Kano's students were using a vacuum filtration to draw these mixtures through membrane filter paper. The liquid passed through the paper membrane, leaving a film of aligned nanotubes on top. In an exhaustive set of experiments, Komatsu and colleagues showed that the alignment of nanotubes in these films corresponded to parallel submicroscopic grooves on the paper. The grooves likely were formed when the filter paper was pulled onto rollers at the factory, Kono said. Komatsu examined dozens of sample filter papers and used scanning electron microscopes and atomic force microscopes to characterize grooves and patterns of grooves. She cut filters into pieces, reassembled the pieces with grooves facing different directions, and showed they produced films with matching alignments. Komatsu and colleagues also used heat and pressure to remove the grooves from filter paper, using the same principles involved in ironing wrinkles from clothing. They showed that films made from groove-free paper had nanotubes aligned in several directions. Finally, starting with groove-free paper, they showed they could use a very fine reflective grating with periodic grooves to create their own patterns of grooves, and that corresponding nanotube films followed those patterns. Kono said the method is exciting because it brings a needed level of predictability to the production of 2D crystalline nanotube films. If the nanotubes are randomly oriented, you lose all of the one-dimensional properties, Kono said. Being one-dimensional is key. It leads to all the unusual but important properties. While Kono's group's films are essentially 2D, as much as an inch in diameter, but just a few billionths of a meter thick, the individual nanotubes behave like 1D material, especially in terms of their optical and electronic properties. The extraordinary optical and electronic properties of carbon nanotubes depends on their diameter and structure, or chirality. Some chiralities act like metals and others like semiconductors, and researchers have struggled for decades to find a way to make large, macroscopic objects like a wire or one of Kono's 1-inch diameter films purely of nanotubes with 1 diameter and chirality. That's obviously the next step. In this study, we still use a mixture of metallic and semiconducting carbon nanotubes with a diameter distribution. The next step is to apply this new method based on intentional groove making using a grating to achieve total control of alignment direction. Kono said his team has made highly aligned 2D crystals from solutions with a diverse mixture of nanotubes. But when we go to a single chirality solution, we were never satisfied with the alignment, he said. Now with this knowledge of grooves, we are confident we can improve the degree of alignment in the case of single chirality carbon nanotube films. Single chirality films could open the door to applications with mind-boggling potential. For example, sheets of pure carbon that convert heat into light with almost perfect efficiency. Marrying such a sheet to a photovoltaic material could provide a way to turn heat into electric power very efficiently, creating the possibility of radiators that both cool motors and electronics while also powering them. Single chirality crystalline films could also be used to study new states of matter, such as exciton, polaritons, and Bose-Einstein condensates, and for applications that haven't even been envisioned, Kono said. At this moment, only a small number of groups in the world can make these aligned, highly dense, heavily packed carbon nanotube films, he said, and the work we just finished, the grooved-assisted work, offers new control. This will lead to better films, new applications, and new science. We are very excited. Wow, right on. I'll leave a link to the full article in the description, and as usual, please like, share, subscribe, and take care.